All right, so we're going to look at a problem of the day here. This is for single slit interference patterns. So what's happened here is that you have a screen where you've put a laser through a single slit, and this graph is showing you how bright the light is along the screen. So in the middle of the center bright spot, it's very bright. So you see this big bright one, and then it pinches off to destructive interference here and here. And this is in millimeters. This got cut off. This is millimeters on a screen. And so this looks like about 3 this way and 3 this way. So you'd have like this entire distance here to here would be like 6 millimeters on the screen. And then there's these subsequent little bright spots. And this should all make sense to you. If it doesn't, you should look at this screencast that's explaining why single slit diffraction occurs. And the equation that goes with it, and so that we understand that it's just theta equals lambda over b, where b is the width of the opening. Let's see what they've given us here. So they have a particular laser that they've given us the wavelength for, 630 nanometers, so that's a red laser. And the distance to the screen is 3.5 meters. And then theta would be from the center over to the first destructive interference part, which I'm going to read that off to say be 3 millimeters. So 3 times 10 to the negative 3 meters is for what I'll call S, using the double slit notation. And then capital D, how far away the screen is 3.5. So you can do an arctangent and get the angle. But in radians at small angles, tangent is the same thing as sine is the same thing as theta. And so we can just go ahead and get that angle by taking 3 times 10 to the negative 3, which would be the S, divided by capital D, which is 3.5 meters. So let's see what that looks like, because they have a little key here for us. So they get theta is S over D, and they have the 3 times 10 to the negative 3 millimeters. That's from the center of the bright spot to the first destructive interference, divided by 3.5. So we get our answer for theta in radians now, 0.86 times 10 to the negative 3. They have a little notation here about it's better to use 2 theta. So let's think about why they might say that. So they say to use 2 theta because to go from here to here and then take that divided by 2, in order to get theta, which is from here to here, would be a good idea, I suppose, because you could be a little more accurate reading these little boxes and everything that I didn't bother to do. Certainly on an IB test, that's a good idea. Here we just estimated this at 3. So let's see what happens next. It looks like they want us to know what most people call A, so they've been using A here, but in the IB equation booklet, please, this is a B. So we have theta equals lambda over B, so that we have B equals lambda over theta. So there you go. Just plug and chug those, make sure that they're both, that this top one's in meters, make sure this bottom one's in radians, and you're good to go, because that gives us the answer in meters. You'll notice that the unit of radian disappears in these situations. It's a ratio, actually, and so it's fine to have that unit disappear here. And that gets us B, the size of the slit. So very plug and chuggish if we understand what this graph is showing us. Okay, so excellent. State 2 changes to the intensity distribution when the central maximum, when the central slit is replaced by one of a greater width. So if we have a greater width, that means B gets bigger. When we have B getting bigger, clearly theta is going to get smaller. So let's see what they do here. Okay, I guess, yeah, they're clarifying for us that lambda would stay the same, and the angle will decrease because B gets bigger, which is obvious in the equation. So that's pretty cool. The other thing I'd mention is that a lot more light's going through, so everything should get brighter. Let's see, are they talking about that? So the principal maximum stays in the same place because it's in the middle, and then everything else comes in closer, and then everything should get brighter. Yeah, okay, so the increase in the intensity of the beam is the other thing. So they want 2 things. And we have two things. So hopefully that helps with this one. And single slit diffraction should be pretty easy to do. There's not much they can do to complicate things with this, unless they have a double slit that's also a single slit, because actually that's what a double slit is. A double slit is actually two single slits. So that's coming our way soon in a near screencast where we'll talk about what happens when you consider the fact that double slits are actually two single slits. So that'll be fun. We'll be doing that in a minute. Perhaps I'll get to that today. We'll see how things go. Any case, keep studying, keep working hard, and make sure you're posting your homework well. Good luck.